Hello and welcome back to the very last section of Unit 2. You're going to find that this last piece is actually just an extension of what we've been talking about with Lewis structures, adding it all up, and this concept is about hybridization. And really, if you want to just wrap your head around the concept of what hybridization is really all about, it's just simply answering how is this supposed to actually work mechanically? What's happening with the electrons because they're going to be sharing actively between atoms to get that bond. For a covalent bond to form, remember they're sharing back and forth, and we have to get these unpaired electrons to match up. So essentially what's happening with hybridization is we're creating room within these orbitals to make it happen. And to do that, we have to hybridize the orbitals. So let's just take a look at what mechanically is happening. And we're going to do this from our electron configurations first. I'll just bring up all three examples so we can see them simultaneously. What happens in beryllium? If I look at the the electron configuration, I have 1s2 and I have 2s2. And so to do this in terms of orbitals, I see 1, 2 electrons within the s2. This is the outermost one, but this is the stable atom. If beryllium is going to be making a covalent bond with something, remember that we do have a 2p sublevel as well that has an x, y, and z axis. And so we've got lots of room in here. It just is unoccupied. But if I bring an electron in, there's nothing for it to pair up with or nowhere for it to go without that. So we got to create more room with that, and we're going to hybridize this. Rather than have a separate sublevel of S and separate sublevels of P with an X, Y, and Z axis, we're going to actually combine all of these to create room for this, and so it's still energy level 2, but I'm going to steal out of the S sublevel and put it into the P sublevel. And so notice I have an SP hybridization. I took out of the S and I created room. Now remember, they're doing this so that we can form a covalent bond, actively share 2 electrons because they're paired up here. Let's unpair those and actually create room to allow for that active sharing back and forth. That's what we call an SP hybridization. All right, then let's look at boron. 1s2, 2s2, and 2p1. All right, so here's my energy level 1. He's shielded off. The active energy level is energy level 2 because it's further away from the nucleus. And notice that boron has one already in the p sublevel. So let's take out of this, split it up, and we're going to make an sp hybridization. But notice I already had one in the p sublevel, so let's put a second one. We refer to this as an sp2 hybridization. And I think you see where we're going with this. When I have a 1s2, 2s2, 2p2, well, I'm going to take out of the s, and I'm going to, we already had 2 here. We're going to take out of the S and put a third one here, and that becomes an sp3 hybridization. All right, so that's the concept of what's mechanically happening with this. And you don't have to, this is the good news, you don't have to do your electron configuration or draw out the orbitals each and every time. Okay? What you can do is just take a look at the phenomenon of what's going on. So let's do this in reverse, and I'll bring reference to this chart in just a moment as we're doing examples here of different hybridizations and what's going on. So let's take a look at an example of an sp3 hybridization. All right, let's take a look at an example of CH4. Now, carbon has 4 valence electrons, and I have 4 hydrogens that have 1 valence electron. Remember, they only want 2 total. And so 4 plus 4 is 8 total electrons. Okay, so here's my carbon. I have hydrogen, 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 and hydrogen. So that's 2, 4, 6, 8. I'm already done. And notice, to do this type of thing, I would pull out of my S and put it into the P. If I counted up, though, 1, 2, 3, 4 sigma bonds, notice that that's an sp3 hybridization. So it's an example of what I just showed you in the previous slide, but it's putting it into action, and you see that we just count them up, and that's all we need to do. Now, there's other examples of an sp3 hybridization. So this was an example of 4 sigma and 0 unshared bonds. There is an example of like a 3 and 1. If we took a look at like ammonia, which is NH3. Okay, to do that, we have the nitrogen itself is going to have 5 total valence electrons, and I have 3 hydrogens with 1, so that's 8 total electrons. So hydrogen, hydrogen, here's my nitrogen, hydrogen, 2, 4, 6, and I must have 8 right there. Okay, so I see I have 1, 2, 3 shared, 3 sigma, but I have 1 unshared. Okay, 1 lone pair, it is still going to be an example of an sp3. And if I take a look, there's other examples like water. If I have H2O, well, this is 6, and this is going to be 2, so it's another example of 8 total electrons. Here's my oxygen, hydrogen, hydrogen, so that's 2, 4, 6, 8. Oh, there's 2 and 2. Okay, those are examples, again, of 2 plus 2 is 4, sp3 hybridization. And there is an example, obviously, going to be when we have just 1 electron, but that's, and 3 unshared, or sorry, 1 sigma bond and 3 unshared with that one. Taking a look at sp2 hybridization. An example here, let's take a look at something a little bit more complex with 2 carbons in there. So that's 2, carbon has 4 total valence electrons, and I have 4 of the hydrogens with 1, so that's 8 plus another 4, and that's going to be 12 total electrons. Okay, so counting this up, I have a carbon. Let's combine it with the other carbon, forming concatenation, and I have hydrogen, 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 and hydrogen. We're getting really good at this game of matching them up, aren't we? 2, 4, 6, 8, 10. Oh, and I must have another set right here. Now remember, this second time it's going, it's basically looking like this. I have a sigma bond and a pi bond, okay? And so I have sigma bond, sigma bond, sigma bond, sigma bond. But around this core, why did I put oxygen? That's carbon. And I have 1, 2, 3 sigmas and 0 unshared pairs going around there. So that's an example of an sp2 hybridization. Other examples of an sp2 hybridization, remember this was a 3 and 0. We have other examples like a 2 and 1, and obviously going to be like a 1 and a 2 when we have a simpler one. But a 2 and a 1, an example of that would be something like sulfur dioxide. Okay, sulfur and oxygen all have 6 valence electrons, so that's 3 total. That's 18 total electrons to account for. Here's my sulfur, oxygen, sulfur, oxygen. This oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. But if I count it all up, 2, 4, 6, 8, 10, 12, 14, 16, 18 total electrons. Okay, sorry, not going to be a double bond in there. It's going to be a lone pair around there. And notice that I've got an extra one. That's what I was looking at. I've got 18 total, 2, 4, 6, 8, 10, 12, 14, 16, 18. But this sulfur is not a full octet. So we're going to share this one. That's what I was doing originally. We're going to share that one back. And so I end up with this for an arrangement. I do have 1 unshared pair around there. And this is my sulfur dioxide. Okay, so I have 2 and 1. Okay, that's 3 total. There's my sp2 hybridization again. Pretty straightforward with them, even though I screwed up with the element and the order that they would be forming their double bond. Let's take a look now at sp hybridization. An example of that would be like just a simple carbon dioxide. I have 4 plus 2 times 6, that's 12, that's 14, that's 16 total electrons. Okay, so 12 right here, plus another 4, 16 total electrons. Carbon with oxygen, 2, 4, 6, 8, 10, 12, 14, 16. Oops, this carbon has 2 and 4, so let's put a shared here and put a shared here. So I end up with double bonds on both sides. Now remember, that double bond has a pi, that just brings it in closer, that doesn't affect its shape at all. So around this core, I just have 2 sigmas, don't I? That's an example of an sp. Notice that I had an example of 2 and 0. Okay, other examples of that would be like a 2 and a 1. Okay, that would be the sulfur dioxide that I just did. An example of that would be a 1 and a 1. All right. Now, next would be an sp3 dehybridization. Now remember, this gets into more complex ones. We'd have to have a 3D available in there, and we'd have to have 5 total electrons to work with. So, you know, you see some different examples of, oh, like a PCl5. Okay, so we have phosphorus, and phosphorus has 5 total, and we have 5 chlorines with 7 total electrons around there. And so what we end up with to get 5 and 0 is, remember, we have this, we have our chlorine, we have our chlorine, we have our chlorine. So that's 1, 2, 3, our chlorine, and then we're going to have one coming right out at us, and that's going to be chlorine as well. And it certainly is going to be all these valence electrons going around in there, and so that's an sp3d hybridization. And then lastly, we have an sp3d2 hybridization that's in there. So you see different examples. The sp3d2 is going to be an example of 6 total electrons, or 6 total sigma bonds, and so an example of that one would be something like SF6. Okay, so we have essentially changed this and changed these to fluorines, but we have this, and then we're going to end up with a second one coming straight out at us, wouldn't we? If we're just going to change that up rather than write it all out again. You can see where we're going with it. So those are pretty simple examples to see into play. Now let's take a look at some sample problems. Okay, here's what it looks like, the first level of it. I'm going to keep this chart up here, but do know that you've got to have this chart memorized. Along with everything, there's a lot of memorization in this chapter. Let's take a look at the hybridization found within CH3Cl. Don't just jump to it, draw it out first. Everything in this chapter, make sure you're drawing it out. So we have 4 total valence electrons here. We have 3 hydrogen times 1, so that's 7. And we have 7 total electrons here. So that's going to be 10, that's going to be 14 total electrons. Okay? And so we go carbon, we have a hydrogen, 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 and chlorine. 2, 4, 6, 8, 10, 12, and 14. Everybody's got an octet. We have chlorines around here, so I counted up. I've got 4 and 0, and I see, oh, that's sp3 hybridization. Let's take a look at phosphorus with the hydrogen. Okay, the phosphorus is valence electron of 5. I have 3 hydrogens, so that's going to be 8 total electrons. And so here's my phosphorus, hydrogen, 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 2, 4, 6, and I've got to have 8 in there, and that goes around the phosphorus. So here I have an example of a 3 and a 1. 3 plus 1 is sp3 hybridization. Now we have sulfur in sulfur with 4 fluorines in there. So sulfur is 6, and I have 4 with 7, that's 28, and 28 plus 6 is 34 total electrons. All right, sulfur and fluorine, 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 fluorine. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, and 34. See, this is where you want to be careful. You got to draw it out first, because you would have thought at first this is 4 and 0. But notice this is an unshared pair. Sulfur is one that's actually getting a little bit extra in there. And so I see 4 sigma bonds and 1 unshared pair. So that's 5 total. And so that gives me an sp3d hybridization. So that's all you need to be looking out for with those. Do your drawing first. I can't harp on that enough in this chapter. All right, this is the last step of it all, guys. And it's nothing more than what we've been doing, but it's answering all the questions. So state the hybridization of nitrogen. Notice that nitrogen in every single case has 5 valence electrons. And so I have 5 plus 3, so that's 8 total electrons I got to account for here. 5 plus 12 is going to be 18 total electrons. Okay, so 5 plus 12, that's 17, plus that 1 lone in there, that's 18 electrons, because this is nitrite. Don't lose track of that guy. And then we have 2 of these. That's going to be 10 total electrons to account for. All right, so now we've done that legwork with it. Let's take a look at nitrogen. And I've got hydrogen, hydrogen, hydrogen. That's 6 total electrons, and so there's 8. This becomes a 3 and a 1, and so that's sp3 hybridization. NO2 with a negative, so the entire thing has one extra electron around there. And so here's my nitrogen. I've got two oxygens. And so that's 2 and 4, 6, 8, 10, 12, 14, 16. And so I need to have one more set of electrons around there, don't I? And so notice I do that. So that's 18. But notice my nitrogen does not have a full octet. So I'm going to share one of these into here, and I end up with a double bond then. Okay, so to draw this out, I'd have oxygen, and I'd have an oxygen, and I'd have a lone pair, and on the outside, I would have one extra electron. Okay, now this is oxygen 1, oxygen 2. A resonance structure would be another double bond over on this one. So it doesn't matter each one, and so it goes either way with those two structures, with the double bond here or my double bond over here. Okay, that's how you indicate the resonance structures. And on the outside, I have my -1. Now, only count sigma bonds, 1, 2, and here's my lone. So that's going to be a 2 and a 1. That's going to be an sp2 hybridization. Last one, we're going to be taking a look at nitrogen. And so short version is this ends up being a triple bond with nitrogen because I have 10 total electrons in there. We got to share them out equally. That ends up being a triple bond. And so I have one sigma, one of those, I'll just call it the middle one, and one on the outside. That's 2 total. That's an sp2 hybridization. Cool. That's a lot of stuff to take a look at. But you notice it's just mechanical. It's exactly what we've been doing before. If you know that chart, it's good to go. Now, I'm going to keep this slide in here about molecular orbitals just because it's looking at the order that these are going to be in, what level. Since they hybridize, they move and they become one hybridized continual one rather than separate ones. But here's the good news for you guys. College Board has gotten rid of molecular orbitals and having to do the drawings with those. I'm going to keep it in here in case they put it back in at some point, but you guys are off the hook for this particular year. So we're going to jump right into our assignment 1 through 6. If you see any questions about molecular orbitals, you can skip them. We don't need to know them. That's going to bring us into the Lewis structures, just practicing those up, take home quiz with it, and practice, 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 getting ready for that ultimate test for Unit 2. I think you guys are going to find a lot of success in this chapter. Taking a look at this unit as a whole, it just keeps on building, building, building. And so I wish you guys luck. Go get them. This is going to be a good one for you.